Now in algebra, we know how to find the domain of any function, and we know that's critical in calculus before we take derivatives. So if I said, let's consider the function f of x equals 1 over x squared minus 4. Now just recalling, the domain are all of the possible inputs I could use, every value of x I can use. A domain is independent of the variable used, it's the actual values. So if I said f of t and that was a t squared, or f of y and that was a y squared, that doesn't change the domain. So in this case here, as long as my denominator is not 0, so basically x can be any real number except plus or minus 2. So in this case here, we'd say the domain is all real numbers except that, and we typically would write that as an interval, negative infinity to negative 2, negative 2 to 2, 2 to infinity. Okay? If I wanted to do a different type of domain, let's say I wanted g of x, and I wanted to do the natural log of 4 minus x over the square root of x. Now that's a little more complicated because I have two different things that I have to satisfy simultaneously. So in my numerator, I need 4 minus x to always be positive, and in the denominator, I would need x to always be positive. And I need both of these conditions true at the exact same time. So in the first case, I would need x to be less than 4, and at the same time, x is greater than 0. That really restricts my domain, and that would leave me basically with x between 0 and 4, or we'd express it as the open interval. Now the key here is, if I have more than one condition that I have to meet simultaneously, you connect them with an and, not an or. An or would be quite different. All right, now let's consider I have a three-dimensional function for the first time. I am interested in z is f of xy, and let's say that this is 1 over x squared minus y squared. I now have a function of two independent variables, x and y. I can no longer state my domain as an interval. Now I would have to state my domain as a set of ordered pairs that satisfy this. So to start off with, my only restriction here would be that x squared minus y squared cannot be 0. So that x squared cannot equal y squared, or x cannot equal plus or minus y. So x cannot equal positive y, x cannot equal negative y. And the way we would state this domain is using something called set builder notation that you probably learned back in algebra but haven't used much since. So in this case, we would say the domain is the set of all ordered pairs, that's how we start, such that, that's what the vertical line means, x is not equal to y, and at the same time, x is not equal to negative y. And we have just described every ordered pair that we are allowed to use for this particular function. If I have another function, let's say g of xy, and that's going to be the natural log of 2x plus 3y. This one's a little bit easier to state because I have one restriction that I would have to meet, and that is that 2x plus 3y would have to be strictly positive. So 3y would have to be greater than 2x, so y would have to be greater than negative 2/3 x. So we would express our domain in this case as the set of all ordered pairs such that y is greater than negative 2/3 x. So this is the simplest way to state a domain if we're in 3 dimensions. Again, we're indicating all of the ordered pairs we can use. Now consider something as simple as a circle centered at the origin, radius 3. This circle is very difficult to work with in a calculus context because it's not a function. In fact, things that are not functions are difficult to take derivatives of and work with in general. But what if I said that everything you could possibly draw on the xy plane is a function in 3 dimensions? For example, consider the following. Consider z equals x squared plus y squared. This would be a circular paraboloid, okay? So what if I said, consider this, and let's pick the value of z that is say 9. So let's say right there, we are 9 units high. Then this circle that I've just carved out is the circle x squared plus y squared equals 9. Not a cylinder, it's the actual circle in 2 dimensions. So if I take something that's 2-dimensional, I can always make it 3-dimensional, and then what we're looking at is a particular cross-section, and this thing here that I just drew is what's called a level curve. So the basic idea that we're going to expand upon is if I said y equals f of x, then I know that f of x minus y is 0. So if I choose a 3-dimensional function, let's say z, well, let's use a different letter, can't use x again. Let's say g of xy, and we said let's define that as f of x minus y. Now I have a 3-dimensional function right here, where x and y are independent variables. Now pick any constant you want. Oh, how about 0? We would get back our original 2-dimensional equation. So we're going to explore this one just a little bit further. Now let's consider this simple 3-dimensional function. I don't actually know what it looks like in 3 dimensions, but I would like the level curve that passes through 1, 2 on the xy plane, meaning I just simply need to evaluate this at 1, 2. And if I do that, I'll get 4 minus 12 plus 4, that's negative 4. So 4x squared minus 3y squared plus 2xy equals negative 4 would be a level curve of this 3-dimensional function at this point. So think of it this way, that on the x, y, z, I have the ordered triple 1, 2, negative 4 that this curve passes through. Now with that in mind, what if I did this with 3 independent variables? Consider I have the following. G of x, y, z is x squared plus y squared plus z squared. This is now 4-dimensional. The number of dimensions is always the number of variables. I have 3 independent variables, and then this would be a 4th variable. If it helps, think of it, call it W if you will. But I have 1 dependent, 3 independents. This is 4-dimensional. I cannot draw this, but I can ask for a particular point. So let's say I want to consider the point, how about negative 4, 2, 4. I want to make that my input. So if I said g of negative 4, 2, 4, I would get 16 plus 4 plus 16, which is 36, meaning x squared plus y squared plus z squared equals 36 is one particular solution of this. But this is not a level curve. This is 3-dimensional. This one is called a level surface. So if I'm in 3 dimensions and I give a specific point, I will create a level curve. If I'm in 4 dimensions and I give you a specific point, I will create a level surface. And I'm going to give you one more example of this. This is something you're probably familiar with from other classes. You've probably all had a geography class, either junior high, high school, or college, where you're looking at a map, particularly an overhead view. So let's say we're looking at this giant area, and each of these rings represents a particular elevation. So this would maybe be a small hill. Maybe this ring here is 1,000 feet, the next ring is 2,000 feet, and the top ring is 3,000 feet. Maybe that ring's 1,000 feet, and then that's 2,000, and so on. So these would represent hills. This one would be the tallest. And what the ring represents is as if I sliced the horizon horizontally, and it's the rim of what's left over exactly at that altitude. So it's very easy to plan if I know exactly the height and the elevation, because I can't draw a model that has 3 dimensions in the picture, so I do these. These are all level curves, and this is generally referred to as a topography map. And again, most of you are probably familiar with that. That's exactly borrowing on the concept that we're using right now with the level curve.